I'm standing in a dark field, and I have a question for you. How do we know which events in the universe can influence us and which we can influence? Or do we? Imagine you're holding a flashlight. The beam represents future events you can affect, while the sounds reaching you from behind are past events that have influenced you. But here's the thing. Where these two regions overlap, we get something called the causal diamond. This space-time bubble is where cause and effect are possible. Picture light cones expanding from a central point. The past light cone shows signals that reached you, and the future cone reveals where your signals can go. It's like the universe's way of saying, you can't sit with us, to events outside this diamond. The speed of light and space-time curvature shape these boundaries. The cosmic microwave background is part of our past cone, while a light signal sent today shapes our future cone. But what does it all mean for us?
In the framework of special and general relativity, a causal diamond is a space-time region defined by the intersection of your past and future light cones over some interval of proper time. The past light cone, the causal diamond, is thus a lens through which we view the causal structure of space-time. Its shape and size depend on how signals at the speed of light propagate through the gravitationally curved fabric of the universe. Physicists use this concept to determine which regions of spacetime are causally connected, i.e., where cause and effect can operate without violating the light speed limit. If you emit a light signal now, the region it can reach within a finite time defines part of your future causal diamond. Conversely, the cosmic microwave background radiation, CMB, that you can observe today defines a portion of your past causal diamond, since it represents the earliest available electromagnetic signals that have managed to reach you. Think of standing in a dark field with a lantern. The area you can light up in the future, the forward reach of your lantern, and the sounds you could have heard from behind, past events that sent signals to you, overlap in a region of mutual influence. This overlap region is like a causal diamond, where your actions matter and other events can matter to you. Light cones are fundamental constructs in Minkowski spacetime, the flat spacetime of special relativity, and retain their significance in curved spacetime, as described by general relativity. The shape of a light cone is determined by the constancy of the speed of light. Moving forward in time, a light signal spreads out in space at a fixed rate. When gravity or large-scale spacetime curvature comes into play, these cones can tilt, stretch, or squeeze, but they never break the rule that nothing can travel faster than light. By combining past and future light cones, the causal diamond demarcates a region where signal exchange and causal ordering are physically meaningful. Example: in a simple spacetime diagram, a Minkowski diagram, your world line, your path through spacetime, sits at the center. The past light cone narrows as you go backward in time, capturing fewer events that could affect you, and the future light cone widens forward in time, encompassing potential destinations for signals you send out. Analogy: picture a flashlight beam in a pitch-black room. Shine it forward, and you see a cone of illumination. Now imagine a second, backward-pointing beam representing signals that reached you from the past. Where these cones overlap forms a finite bubble of mutual visibility and influence, a geometric portrait of causality. A causal diamond, by itself, is not a time loop. It merely defines causal reach. Time loops arise if there are closed Timelike curves, CTCs, paths in spacetime that loop back onto themselves, allowing an observer to potentially return to an earlier point in their own history. Solutions to Einstein's field equations, such as those proposed by Kurt Gödel or involving rotating Kerr black holes, show that CTCs are mathematically possible, at least in theory. If such curves existed within your causal diamond, you might experience events repeating, giving the impression of being trapped in a temporal cycle. Example: consider a hypothetical wormhole connecting 2 points in spacetime. If one mouth of the wormhole is moved at relativistic speed and brought back, it may create a scenario where traveling through it sends you to your own past. This hypothetical construct introduces a loop in your causal domain. Analogy. Imagine a hallway where walking forward always brings you back into the same room you started from. No matter how many times you walk, you end up repeating the same path. In spacetime terms, that hallway is like a closed time-like curve. Your timeline bends back on itself. On cosmic scales, the concept of eternal recurrence or cyclic cosmologies raises another form of looping, not literally traveling back in time, but having a universe that goes through repeated cycles of expansion and contraction or repeated phases that closely resemble previous ones. The Poincaré recurrence theorem suggests that certain finite, isolated systems might eventually return to near-identical states, given enough time. While this isn't a true time loop, it hints that if our causal diamond were to encompass the entire cosmos and the universe repeats its patterns indefinitely, we might witness recurring conditions that feel loop-like. Example, in Penrose's conformal cyclic cosmology, CCC, the universe resets after immense timescales, passing information from one eon to the next. While not a direct loop in individual timelines, from a grand perspective, patterns repeat, mimicking a cosmic rerun. Analogy. Think of seasons on Earth. Each year you see winter, spring, summer, and fall return. This recurrence isn't you traveling back in time, but the environment cycles through similar states over and over, giving an illusion of repetition. The second law of thermodynamics introduces an arrow of time by stating that entropy, disorder, tends to increase in a closed system. This arrow makes time loops problematic. If you were trapped in a perfect time loop, you would encounter the same low entropy configurations repeatedly. This contradicts the idea of relentless entropy growth. The thermodynamic arrow thus acts as a conceptual shield against stable, perfect time loops. Physicists suspect that any attempt at forming a loop would break down under quantum or gravitational instabilities, preventing a perpetual cycle of identical events. Example, a broken glass that never reassembles itself spontaneously into a whole glass without external intervention exemplifies the arrow of time. A true loop would require reversing such irreversible processes. Analogy. Imagine an egg dropped on the floor. It breaks, increasing entropy. A time loop scenario would require the shards to spontaneously reform into a perfect egg repeatedly, something never observed in nature and at odds with fundamental physics. Quantum mechanics adds layers of complexity to the idea of time loops. At the quantum scale, the laws become probabilistic. Even if a time loop existed, tiny quantum fluctuations would accumulate differences in each iteration, preventing a perfect cycle. Moreover, Stephen Hawking's chronology protection conjecture posits that the laws of physics might forbid stable, closed time-like curves to prevent logical paradoxes like the grandfather paradox. Quantum effects, vacuum fluctuations, and exotic matter requirements for building closed time-like curves all suggest that stable loops are extremely unlikely, if not impossible, within known physics. Attempts to form a time machine using wormholes run into the need for negative energy densities and special quantum states. Such conditions are speculative and may be forbidden by yet undiscovered principles. Think of trying to keep a spinning top balanced forever on its tip. Tiny vibrations or quantum fluctuations will eventually topple it. Similarly, even a slight quantum nudge would derail a perfect time loop. We observe no direct evidence of time loops in our universe. Astronomical observations, cosmological data, and particle physics experiments show no signs of cyclical timelines on accessible scales. The universe's expansion, governed by dark energy and matter distributions, appears to evolve forward. If time loops existed commonly, we might detect anomalies, strange gravitational lensing events, inconsistent cosmic histories, or repetitive astrophysical phenomena. Thus far, we have none of these. Example, measurements of the CMB and large-scale structure formation align well with a straightforward arrow of time extending from a hot, dense early universe toward increasing complexity. No observational hints suggest closed time-like curves or repeating global states. Analogy. Imagine reading a very long, detailed novel. If a chapter repeated word for word somewhere far ahead without explanation, you'd notice. Similarly, a cosmic time loop would likely leave telltale signatures. We find no such repeated chapters in our cosmic story. The idea of being trapped in a time loop provokes deep philosophical questions. If loops existed, would free will vanish as every decision repeats itself infinitely? Determinism might reign supreme in such a universe, with no true novelty. However, physics currently suggests that while certain exotic solutions to Einstein's equations allow loops, they likely remain mathematical curiosities. The forward-moving arrow of time, combined with thermodynamics and quantum uncertainty, supports a universe of genuine progress rather than eternal repetition. Philosophers have debated eternal return for centuries. Nietzsche's concept of eternal recurrence challenged individuals to imagine living their lives repeatedly. Physics, however, points toward no such actual recurrence. Think of a record player's needle stuck in a groove, looping the same segment of music over and over. Philosophically, this robs the song of creativity and depth. Physically, our universe seems more like a live concert that never exactly repeats a performance. Causal diamonds define who can influence whom in spacetime. While they set the stage for discussing causality, they don't by themselves create loops. Theoretical constructs like CTCs hint that time loops are possible in certain exotic solutions, but known laws, entropy growth, quantum uncertainty, lack of observational evidence, and plausible chronology protection principles stand firmly against stable macroscopic loops. Ultimately, we're left with a universe that appears to evolve forward in time, not one that traps us in repeating cycles. The study of causal diamonds and hypothetical time loops pushes our understanding of gravity, quantum mechanics, and cosmic structure, testing the boundaries of known physics. Example: just as no perfect perpetual motion machines exist, no verified physical process creates perfect time loops. Analogy: a causal diamond is like a stage on which a play is performed once, influenced by past acts and setting the stage for future ones. Time loops would be like the same play performed identically, forever. Reality, as far as we know, writes new scenes continuously, never endlessly repeating the old script.